Thank you very much, Michelle. I just put my password into my computer and start it up. Can we switch over to... Thank you very much. So, good morning, ladies and gentlemen. I'm here to give you a bit of a rundown on what we're thinking about neurodegenerations and how we're proposing to perhaps slightly change the game in terms of the way we think about these neurodegenerations, particularly those related to dementia in the first place, and what implications that might have on target definition and drug discovery. The Human Brain Project is large. During the course of this talk, I will give you insights into the way it's organized so that you can perhaps take away with you also a more global view of it. But I will try to be a little more specific in relation to pharmacology and the pharmaceutical industry for the purposes of this talk. So, essentially, the main postulate is that neurology has, clinical neurology and probably clinical psychiatry has reached a brick wall. Over the last, I would say, 20 years, I've been banging my head against this in the sense that pharmaceutical industry put a lot of money into stroke, put a lot of money into dementia, and have pulled out of stroke and are pulling out of dementia. And the reasons for that were unclear until it became an insight, a communal insight of quite a number of us, that we were still working with the techniques of Paul Broca of the 19th century, in other words, describing. So if you make the analogy with Linnaeus, I think we've done that, and now we need to go forward. And of course, changes like the description of the human genome gave us great hope that at last we were going to get into mechanisms and mechanisms at the most basic level. And there also we're now beginning to see that nature is more complex than we feel, than we think, and than we feel actually. And that, post-genomics and so on are going to be extremely important. And the reflection around the Human Brain Project has essentially gone from there. And the central idea is that we must now move on from descriptive diagnostics to mechanistic diagnostics, and how can we do that, and is it now the time to do that? That's what we're going to talk about. And we're going to use just as an exemplar the dementias, simply because they are a great social problem. They're a personal problem for many of you and for me. They're an economic problem for our continent and probably for the world, with our aging populations and with the need to support these people at the end of life in a humane and reasonable way, or to be able to prevent the disease or treat the disease. So there are two-pronged attacks. Either we're going to do this societally, or we're going to do it scientifically, or we're going to do a mixture of the two. And these are the outstanding questions that I think are still with us, and which we haven't addressed before pouring large amounts of money into drug development. Can we diagnose it? The latest evidence from Tom Beach, the pathologist at in Arizona who controls all the NIH studies, is that we do not diagnose Alzheimer's disease accurately in something like 25 to 30% of cases in life if you use the endpoint as being pathology. Do symptoms matter? The brain has a very limited number of ways of expressing itself, in the sense that those who measure that expression focus on a small number of things. Our interactions are highly complex, but we don't have measures of those complexities. We have measures of very simple aspects. Do you remember a five-letter number? Do you remember it backwards? Blah, blah, blah. What weight do we give to pathology? Is the pathology at end of life any indicator of what has happened during life? What about carriers? People who have the pathology but who compensate, who take advantage of the fact that the brain is an extremely redundant organ. You all know the fact it needs 70% of nigrostriatal cells to degenerate before the first symptom arises. So is it possible that treatments can be found in preclinical phases. That would be a radical change. And if so, can we diagnose the thing preclinically? Which means then eliminating pathology in a sense as an endpoint. And why don't our current treatments work? So the causes. We have little idea about the mechanisms of the causes of dementia. We know a lot about the biology of tau transport, amyloid degeneration, amyloid clearance, and so on and so on. What is the role of genes? The classical thing of only 10% of the cases being apparently monogenetic due to monogenetic abnormalities. Are these proteins which are deposited really abnormal? Amyloid has been reported to be an antibacterial in science. And why do we always go for the next thing that's been discovered? You remember acetylcholine. You remember everything we spent on that. You remember how NICE responded to that. Now we've done the same with amyloid. We clear it. Nothing improves. Next we'll be doing tau. Then we'll be doing presenilin. This is what I call lamppost science, which essentially the next thing you find you go for. And they're all predicated on a very ancient idea, which is Ehrlich's bullet, that you'll find one drug which will cure the thing, or at least make it better. Whereas even in those diseases where we have causes like infections, we tend to give 3 or 4 drugs at a time and then rotate them because otherwise you get resistance. None of those concepts come into our ideas about the dementias at all. Here's a little reminder from Kertész in Brain, 2005. This is a group of frontotemporal dementias of the behavioral variant type. So clinically quite precisely defined. And as you'll see, of these 32, only 6 maintained that syndrome through life over the roughly 8 years that they were followed, and they had a variety of pathologies, including Alzheimer's disease, motor neuron disease. Of the remainder, there was a second syndrome, and you can see the second syndrome was really sometimes quite different. And then of the remainder of those, there was a third syndrome, and they're not a minor remainder, they're 12 of the original 32 went through a third syndrome before coming to pathology. So really to base everything on description of pathology at one time point, it's a little bit difficult. Okay, so let's see now why we should think that clinical neuroscience is at a tipping point. We start from syndromic diagnosis, which I believe, and I propose to you, has reached its limits. And I suggest that what we need is a mechanistic or causal diagnosis. Wherever we found causes, we found cures. HIV took 10 years to find the cause. The cause was very strange, an unknown mechanism prior to HIV. We now have treatments which mean that everyone that gets it lives, whereas when I started in neurology, everyone who had HIV died, and died a terrible death. So causes, I think, are absolutely fundamental. The first issue is, are we helped by the deciphering of the book of the human genome? Well, the first thing is that there is a lot of information out there about the human genome and about the human genome in neurological disease. And you could get a postdoc simply to go to the public Library of Medicine of the United States, get them to use a data mining procedure with neurological disease and any mention of genetic abnormality, and you could draw a picture, a multidimensional picture of the human neurodiseasome, if you like. So what you have here, the details are not terribly important, but a lot of disease groupings and a lot of mutations and haplotypes, all of which are related to each other in some way in this multidimensional image, and some of them are very strongly related to each other. So clearly there are genetic bases to some of these diseases, but they appear to be not particularly unique. Some of you may have seen the recent study published showing that of the 5 major psychiatric syndromes, the GWAS studies suggest that there's a group of genes that are related to all of them, not by diagnosis, but simply due to the fact that there is a psychiatric condition. So clearly there's a lot to be done here. This is half a day's work by a postdoc. This is big data approach. So I think that here we have a potential avenue down which future research could continue. We have modern neuroimaging. increasingly sophisticated, in fact very sophisticated now, essentially pathology in life, where that pathology can be either fibers, so connectomes, it could be structure, and structure of various types, local water concentrations, myelin concentrations, water mobility, ion deposition, all of which are of potential use if found in the brain during life, never explored in terms of the development of the diseases. And then the various anisotropies. You could also have functional magnetic resonance imaging, positron tomography with specific markers. You just have to know which marker to go for, so I think that's a second line issue. So there's a possibility of following pathology in life, which gets it away from the problem that pathology after death is an end stage. And if we're going to deal with treatments, then we need to know pre-end stage, otherwise we're never going to be able to treat something. If you treat the end stage position, then you may not be treating what's necessary at all. We're getting much better at diagnostics using neuroimaging. So this is the application of modern statistical techniques. These are machine learning techniques. So these are used for the interpretation of structural images, simple 1.5 or 3 Tesla clinical images, where we got some friends to send us pictures of people who had post-mortem Alzheimer's disease and people of similar ages who had post-mortem no Alzheimer's change, who were normal, could have had Alzheimer's change. As you know, there are a lot of normal people, when they die, there is some Alzheimer's change, which is compensated. So we wanted to really try and dissect out the two. Now, you remember I told you Tom Beach found a 25 to 30% misdiagnosis rate for Alzheimer's disease. These are the correctly classifieds, using these two groups of patients, using a support vector machine. And here's group 3, which was defined purely clinically, not with the pathology. It's down to 80% that predicted by Tom Beach, or in that range or so. And with really high sensitivities and specificities, much better than a week spent at Johns Hopkins or UCL here, or UBL, or one of those around here as well, and the CHUV and other nice places like Salpêtrière and Montreal and so on. So new ways using high-performance computing, which you can still do on one of my Air Macs, give you diagnosis which is better than can be done clinically. And you can go on and do some very interesting things. You could look at the scores, for example, of your psychological tests that you use for diagnosis and test them against the prediction of whether you have the diagnosis or not, done using these computer-aided imaging techniques. And you can see some of those scores have absolutely no relationship between predicted and real, whereas others have very tight relationships. So you can refine, this was a backwards and forwards movement between the clinician and the computer-aided radiologist and so on. But always, always, the computer-aided radiology is better than the radiologist. Now, that's not to say that there's no need for a radiologist, in fact, far from it, because there are all sorts of other things that need to be excluded. The radiologist is aided by these techniques. And then one can get down to really specific connectivity. For example, here's a study which was done quite recently from our lab back in London, when I was still in London, looking at the connectivity of the subthalamic nucleus in relation to treatment of Parkinson's disease with deep brain stimulation. And what you can see is that the connectivity is absolutely remarkable. We started off with a data mining procedure from 1945 to 2011 of all the connections between the subthalamic nucleus and other parts of the brain. They are enormous. It's just an oversimplification to talk about 2 or 3 areas which project to, or which are projected from, the subthalamic nucleus. Subthalamic nucleus has divisions itself, it has inputs, it has outputs, and all these have now been described in the human in imaging terms. So the sophistication is very high, how to integrate all this. Then there's the achievements of modern neuroscience. Now, some of you are of the age where you'll remember that modern neuroscience is very modern. It came into being during our lifetimes. Neuroscience was part of physiology previously. So if we say we've had 30, 35 years of real modern neuroscience, that's about 3 million papers out there. But the real problem is that all this information is very fragmented and very atheoretic. Here are just some of the ways that we can look at bits of the brain at various scales. These are spatial scales, but there are also, of course, temporal scales, be they subcellular, molecular, cellular, tissue, whole brain. And the way we go about doing this science is traditional, it's reductionist. We're working here not with non-organic matter, we're working with organic matter, yet we've gone for it in a reductionist way. Perfectly reasonable. All the achievements of genetics, the DNA code and so on, came from that sort of hypothesis-led science, though I think possibly what Watson and Crick did was not quite as reductionist as people seem to think, because there was a lot of data they were trying to interpret. They were scouring the data for an inner pattern. And we don't do that with our neuroscience, which deals with organic matter, living matter, which constructs things. It constructs from 4 bases everything that we're doing just at the moment in terms of memory, language, and everything else. And we teach our students to get involved in one particular way of looking at the brain, and we go in great depth, and they have no idea about the rest of what's happening in the brain. And the fact of the matter is, we have no idea about the rules that define the relationships between the different scales of organization of the brain, be that functional or structural. Well, when I say no idea, that's not entirely true, because here are some of the ideas, what we call rules. And one of them you could see is Hodgkin and Huxley. That's 1948. They were already describing in mathematics the way that the saltatory conduction of the nerve impulse goes down a myelinated nerve. And there are lots of other now examples of these sorts of rules that define the distribution of ionic channels, that define the flux of ions and so on. And we also have a lot of rules about the structure. So here you have a standard column, and you have the organization into 6 areas, 6 layers. And then there's plenty of information in the current literature about the densities of connections coming in, coming out, the different types of neurons you find in each of the layers. So that can all be defined in probabilistic terms, in statistical terms. And then you can start creating models. And the Blue Brain project of Henry Markham has done this. It's done it for a rat. And you can then test it in vitro against in vivo. And you can see that the responses in vitro and ex vivo, really, it's slices of brain, that those responses are identical. Look at the evidence. And then you can stimulate them electrically. And again, look at the evidence between left and right here. The responses of 2 real neurons and 2 in silico neurons given the same inputs and showing the same outputs and showing the same biophasic responses. So the ability to put together these rules that define the relationships between different levels of organization and their ability to predict what's going to happen if you perturb them or stimulate them is therefore, in principle, an extremely viable way of doing things. The question is, can we do this in something of the complexity of the brain? And in something of the complexity of the brain. And this is really what we're trying to do. We're trying to go from the very lowest levels up to the very highest, trying to understand how the different layers, be it genetic code, proteins expressed, ionic channels, synaptic organization, network production, coming up through the meso to the macro organization, the systems, and then finally emerging as the cognitive component. All these things are extremely important, and we feel that we can now do this, and the question is, how can I justify that? So the aim, the perspective now is to integrate theoretical concepts for animal studies, human images, neuroscience research from the molecular all the way up to the cognitive, try to bring them together in some way, so federate the data that exist, integrate the data that exist, and try and get bridging between these scales of organization so that we develop a theory of the brain. I mean, you know, the physicists are really fantastic because they have this massive CERN, and they also have a theory of how matter is organized. They can do single experiments, which are absolutely defining in terms of how we understand non-organic matter. There's no reason why we shouldn't be able to do the same with organic matter. And what is it that enables us to do this? Well, I think it's essentially advances in information technology. And it's at that point that my computer stops working. Let me just see if I can. Well done. See, you can repair anything. So modern information technology. I don't have to tell you about it, but I'm going to remind you what's happened in the last 10 years. Firstly, we started off with von Neumann machines, so we're very limited. We're not going to do with a von Neumann machine what the brain does, because it's not a von Neumann machine. So what we want to get to is neuromorphic computing. And this is why one part of the Human Brain Project is also high-performance computing, because the computing experts are going to give us the tools to federate and integrate the data, the legacy data that we have, but they also want to know the principles of brain function, because they want to move from the silicon chip working as a digital machine to something that is more neuromorphic. And there are already in Heidelberg, Karl-Heinz Meyer, who's the third of our co-directors, directing the third pillar, he's already manufacturing neuromorphic chips, which work essentially on statistics rather than on binary logic. Moore's law. You all know Moore's law? Every year, twice the power. They've hit a brick wall as well. We want to get to exascale to be able to do these simultaneous equations that will define the functioning of the human brain. Exascale is 10 to the 18 flops per second. Okay? For that, you need a power station that could probably run the electricity needs of half of Lausanne. So this is monstrous, because it's matter. It's doing the same as this. This only needs the caloric equivalent of 2 bananas a day. That needs a power station. There's something clearly wrong, and there's some clear scientific challenge there. And this is the big challenge of the Human Brain Project. So we need to go from those energy limitations in order to be able to go beyond exascale. But what have we got? We've got bandwidth and routing, which was unimagined 10 years ago. We've got distributed database managements, which were in the eyes of the research and development teams at Oracle and other places 10 years ago. We've got cloud environments, which have jumped onto us in the last 3 years, no longer. Database querying and addressing. Google, 10 years or so, not much longer than that. Facebook, 10 years or so. Remote. At the EPFL, we have engineers who are now saying, well, what we could do is we could construct infrastructures which will address every bit of hospital data in the world and every bit of neuroscientific literature, and then we'll be able to anonymize it, we'll be able to do a first level analysis to give you metadata, go through a second anonymization procedure, and come into some central area, or even to an individual at his desk with new software written to allow real-time analysis on supercomputers on a little machine like this, which is not possible at the moment, in order to be able to analyze the metadata and then scrub all the metadata, thus guaranteeing everyone's anonymity and privacy. So they're now working on those things and they're showing proof of concept day after day. And then finally, this sort of real-time visualization, which IBM and Cray are working on at the moment, and which all sorts of other people are as well. So clearly the time has come. Out of this supercomputing has come a completely modern mathematics as well. All these machine learning techniques I've already spoken about, all the nonlinear mathematics, which is also allowing us now to... This has been in use in other industries for the last 15 years. The nuclear industry, there's a lovely story about a French radioactive processing plant that was losing a little bit of radioactive powder every so often, which required the École Normale Supérieure mathematicians and the first or the second generation of Cray computers to find the causes of. The cause for the crash of the A320 in India, the cause of the Columbia disaster, have all been done with this sort of predictive modeling using high-performance computing. So other industries and other parts of science have already done this sort of thing. So there's no reason why, as neuroscientists, we shouldn't. Indeed, my proposition is that medicine, probably dragging down neuroscience by its conservatism, means that we are the last to take advantage of the advances in computing, in science, research and development, of all the sciences that exist, the last. And we should be ashamed of that. Okay, so what we need is a high-level challenge. And the high-level challenge I'm proposing is a major paradigm shift from phenomena, from descriptive syndromic diagnosis to biology. What is wrong? What is at the basis? Because only in knowing that will we know what targets to go for. Now, the MOAE, you all know what an MOAE is, presumably, in this land of acronyms. Who knows what an MOAE is? You don't know what an MOAE is, do you? No. It's the mother of all experiments. So in this mother of all experiments, which is the second mother of all experiments I've done in my life, essentially we've got lots of Alzheimer's patients and healthy controls. It took me a year to convince all the people to do this. Philippe Amriel gave me all his genetic data. The 3Cs group in France gave me all their imaging and behavioral data and such like. Sanofi Aventis gave me 400 scans from a failed clinical trial from the placebo side. And people are offering their data at the moment, because the aim of this, in the end, of course, is you put your data onto your computer, you have the HBP infrastructure server in your lab, and everyone can access your data as soon as it's generated. And in return, you can access anyone else's data. Just think of the savings on experimentation. Think of the added value for every single piece of data. Think of every Minister of Health in Europe who pays to have your scan done and then put on a PACS machine and never used again. And when you say to him, do you know the added value of this? It's 36% per annum in perpetuity, as the Wellcome Trust showed. That's the result of investment in biomedical research. So what politician is going to say no? What citizen is going to say no when he says, here's my money, what are you going to do with it? Oh, you're going to look at my brain, well, that's very nice, I love that. Oh, you're going to do research, you're going to help my children when they get their diseases? Yeah, I mean, it's simple. You just have to get that across. So here's the experiment. We got all these things, scans, clinical scales, measurements, genes. There were almost 500,000 SNPs involved in quite a lot of these. Incomplete data, non-normalized data. And it's frightening, isn't it? But of course, there is mathematics to do all this. In a predictive model, generating a pattern which represents entities which are homogeneous in terms of their biological basis. And the algorithms, there are a number of them. This is a French algorithm called Hypercube, which deals with all these problems, which is non-Euclidean in its approaches, non-stochastic. We're not used to this because in biomedicine we're used to what I call end of college univariate statistics. All right, multivariates come in over the last 10 years, but you know, correlations and p-values and wonderful things like that, which you teach before you go to university. And everything we're taught at university, somehow we don't seem to be able to, bring in. So here you have, this is just a scheme to show you that you have your data sources and your learning matrices and some data audit and rule builders, and you launch the program, highly, highly, highly computer intensive, not on supercomputers yet, already performing reasonably well, as you will see. You get sets of rules which essentially define different homogeneous groupings of patients with similar causes, because this is not correlational, this is causative, predictive, perhaps would be a better word. And then finally, you discover what sort of groups you have. And here's a pilot study used from 200 subjects from the ADNI database. And just look at where the colors are. The different colors define different groupings. And look at the areas that are involved. And immediately you think dementia, even without knowing it. Different types of dementia, frontal areas, medial temporal areas, precuneate areas, in different combinations. So that was the first little experiment. Now we've started doing experiments with the 5,000, and we're beginning to find groupings of people who have similar rules, which can be either data rules or combined together to give rules related to normality or to the Alzheimer group. And you can see that those rules are relatively homogeneous. Around that central one, which is the big dementia one, you've got, we find things like amyloid, APP, we find some very curious associations as well. And in groups of 6, 7, 8 of them, they define one of those discs. A blue disc, normal, a pink disc, different type of dementia. And so we're moving forward with this. This is totally preliminary work at the moment. I'm really only talking to you about it in practical terms rather than giving you proper data, because it is work in progress. But it's already clear to us that this approach is going to give fruit. So we're generating these disease signatures, which are the equivalent of mechanistic and causative diagnoses, essentially. And so what do we want to do with our medical informatics pillar? Data federation, integration, data mining, doing this sort of predictive causal modeling, finding the biological signatures of disease, and then it's not a good thing to do just dementias. What you would like is the whole of brain disease, psychiatry, neurology, everything. Because the bigger the dimensions, the bigger and the more data you're going to be able to bring in, the better is going to be the definition of these groups, and the more sensitive the technology is going to be. But we have to start somewhere. And then, when you get a signature of disease, you'll have candidate genes. So you go and see the geneticist, the omics expert, and you'll ask, what system is involved? What do these genes tell you about what system is involved in the brain? Biochemical system, if you like. And then we'll go to the doctors and we'll say, well, these different groupings defined in terms of biological basis, what is it that differentiates them now in terms of their symptoms and syndromes? Are the symptoms and syndromes adequate, or do we need to look at different symptoms and syndromes? So that'll be deep human phenotyping. We'll then go to the pharmacologist and we say, look, this is the system, the biochemical system that is involved. You've got everything under the sun in your pharmacopoeia to get them fiddle around with this system. Let's get a model and let's start fiddling around with that system. And not with one drug, but with multiple drugs. I've seen experiments now which suggest that if you did tenfold less than therapeutic doses of drugs and combine them, you get a 100-fold increase in activity in animal models. I can't tell you any more than that for confidentiality reasons, but the interactions between drugs have never been thought about, and yet these systems are highly complex and maybe multiple that are affected if this is some very basic disorder. If it's an infection, which, you know, I'd challenge any of you to tell me that Alzheimer's disease isn't an infection yet. I don't think that's been proven. Indeed, there's lots of suggestions that it starts somewhere and then spreads. There's imaging data for that. There's now coming forward EEG data for that. There's data even from phenomenology of that sort of process occurring. So, you know, we really need to get into the biology of this. Then we'll have the target identification, and then you'll have your clinical trials, and also every single patient going to the hospital will be in your clinical trial, because the diagnosis will have been improved massively. And so you will be able to work on homogeneous groups of patients, and they may be homogeneous groups of disease patients or normal subjects or whatever. And so the whole thing should become much more efficient, much cheaper, much more rapid, and screening for drugs may well become a problem of the human and not a problem of the rat. So that then we can generate our models in order to look at the basic biology, but the model for the drug will be the human. And God knows if we haven't missed out on hundreds of drugs by testing them on rats swimming around in Morris mazes instead of taking them straight to the human. So how do we put all this together? Well, we're going to have the brain atlases, call it that from the predictive modeling of the human brain. We're going to have configurations of various aspects of the brain in terms of data and in terms of rules that we develop. From the other side, we're going to have our diseased brains. And using our clinical data, we will also, using essentially the same sort of brain reconstruction workflows as used on the neuroscientific data, we will develop also specifications, almost prescriptions of what the disease state, how the disease's state is configured in terms of these parameters, and what the changed rules are here. So in effect, it'll be like a prescription, a continuous comparison between the diseased and the normal. If they don't fit, then we'll have to go back and reiterate on the normal, or we'll have to define clearer and clearer what happens in terms of the disease state. And then you'll have your model of the healthy brain, your model of the diseased brain, multi-level biological signatures of disease, and then all the various other issues which you're already perfectly au fait with, more than me, target identification, but you'll have help in all of this. Side effects, you'll be able to test the drugs virtually on the model in silico of the brain to see what other systems are affected and where the likely side effects will come from. The binding kinetics you will be doing, the clinical trials you'll be doing on groups of patients, which are much better defined. The preclinical trials, you probably start eliminating this. And your drugs, you'll be able to screen much more rapidly. So the Human Brain Project is about future neuroscience, future medicine, and future computing, and the interaction between these. It's based on all the advances in computing science, neuroscience, and medical science that have occurred over the last 30 years. It's right at the beginning. There are interesting preliminary data. The young people that I talk to are all hyper excited by this, much more than the old folk like me. And we have to think how we're going to train them, because the doctors of the future are going to need skills which we don't have. They're going to need skills in mathematics, they're going to need skills in statistics, they're going to need skills in high-performance computing, etc., etc. So our curricula in our universities need to start adapting. And so this is why this is a grand challenge for Europe. And this is why Europe needs to get involved. And it's not easy to show you whether it's going to work or how it's going to work. It's the same thing as the race to the moon. They got there. But actually what was important about it was all the spin-offs. And that's what's going to happen here, absolutely without any doubt. Lots of people have contributed from my lab and from Henry's lab and from the lab of Karl-Heinz Mayer in preparing all this. And in the end, we're left with this. And I thank you for your... it's a philosophical slide. Any questions? Sorry.
You are ready to take?
Yep.
So if there are specific questions to Richard, they can be raised now. We have time for one or two questions. I see two here. Perhaps first Maria, and then can we have a microphone?
There's a microphone here. Do you want to use this one? Yeah. It's actually quite a good one. So.
Hi, thank you so much. My name is Maria Isaac, and I am a regulator from the European Medicine Agency. My question to you is, we are people coming to us to develop drugs for brain diseases. I agree with you, it's brain diseases. And how long is it going to take you to put all of these together?
What do you think?
I don't know. You are the one that you are organizing this, because we are making decisions every month.
Well, the European Union is at the moment telling us how we're going to do it. So we are told that we have an initial ramp-up phase of 2.5 years to get the infrastructure in place. So there's 6 platforms we're constructing. I think 2.5 years may work. It may need more. I'm delighted to be told and given a target to go for. I think it's probably realistic, given that I'm now working without any money and with people and their goodwill in order to start up all that work. But we'll have to see. Then there's a second phase of 7.5 years. At 7.5 years, all the basic principles should be in place. So at the end of 10 years, we should have a very good idea of what's up. We should have brought life sciences into the computer age. We should have trained a cohort of people who are able to use these techniques. And if the predictions are correct, pharmacology will have changed completely, pharmaceutical discovery will have changed completely, the interaction between basic geneticists and cognitivists will have changed completely. Now, you might say, well, that's ridiculous. So all I say to you is, how long did it take Google to become a billion-dollar company? 3 years, 4 years? I mean, you know, it is not ridiculous. But you have to take the risk. Up till now, the only people in the world who are able to take risks are Americans. I would quite like to see a bit of a European risk. After all, we were the ones who went to America, so we took a big risk there.
Okay. Please identify yourself first.
Thanks, sir.
Thank you very much for your talk. From the University of Maastricht. I very much agree with you that we obviously have reached some roadblocks in drug discovery and also in basic science in last years. Two things that I would like to throw into the round for discussion is, the first one is, are we really following the right approach by saying there are brain diseases? I mean, isn't that one of the major mistakes that we have been doing in the past years, that we've been saying there are cardiovascular diseases, there are brain diseases, there are immune diseases and so forth, and what we're actually learning is that some of these silos of organ-based thinking have actually prevented us from making the real discoveries. All the low-hanging fruits have been harvested, but how about, you've been talking about Alzheimer. One of the major risk factors of Alzheimer and of coronary artery disease are identical. Age. Alzheimer have age, elevated cholesterol, hypertension. These are all identical risk factors between Alzheimer's and cardiovascular disease. Well, so how about if Alzheimer, for instance, is a vascular disease?
I agree with you except for the last thing, because that was the first thing I did in my thesis in my life, and I proved that it wasn't a vascular disease. But quite apart from that, I think dementia is a multi-disease syndrome, very often. It's a diabetic who's got a few strokes and who also has Alzheimer's change. But let's go to the principle of what you're asking. Silos are definitely bad for science, and that's been proven many, many times. But you have to start somewhere. So I mentioned as I was going through that we were using Alzheimer's disease as a starting place, but we knew that you needed to put all of the brain diseases together, psychiatry and neurology together. Psychiatrists are in a very interesting position because they don't have this precise nosology, they just have the few big groups, and they worry about that. We have this precise nosology and we worry about that. And in the end, we've discovered over the last 10 years that we need the geneticists. But even with the geneticists, we're not there. Huntington's disease presents psychiatrically, neurologically, with tics, with behavioral problems, depending on the individual. It's all the same mutation. So clearly we need an underlying theory. I think that's the basic problem. And that theory depends on all sorts of science. It depends on non-silo science. It depends on the ability to do the analyses. It depends on lots and lots of things, as I've described today. So I entirely agree with you, but I think you have to get there. In order to get there, we have to get your concept across. I think we're getting your concept across because Europe has invested $1 billion in your concept. So let's do it.
Okay, so you would agree it may help to actually look beyond the brain.
I think you're very perspicacious.
The other point is...
Please short.
Yeah. The second point that I want to make, I mean, this whole IMI is about public-private partnerships. I think something we also need to openly address is the problems that currently exist in academic research. I think you have seen the papers published last year in Nature and this year in PLOS Medicine that 70%, Genentech says even up to 90 to 95% of all academic research is not reproducible. So I think we have a huge quality issue in academic research, and the reason is that academics and careers are usually fostered and funded based on two criteria: publications and impact factors, and income from grants. I think we need, if we're really serious that ultimately we want to cure diseases, we have to make these outcomes career relevant for medical researchers. Okay. As long as publications, filling papers, pages in journals, and basically acquiring money and spending money. Let me please finish that thought. I think I'm very serious. I'm not polemic here. I'm very serious about this. Thank you very much. Let me please finish that thought. I'm very serious and enthusiastic about drug discovery, but I also believe we need to fundamentally change something, especially when we talk about public-private partnerships, What are we actually doing? What are the outcomes that we are eventually rewarding?
You clearly have an excellent agenda there. I think I disagree with some of that. And the reason I disagree with it is as follows. Firstly, the pharmaceutical industry recently has pulled out of a lot of drug discovery and is going to startups and is going to academia to find the drugs, to buy up the patents and in order to develop the drugs. So your own industry, are you an industrialist or an academic? University, I'm sorry. So the industry is changing its paradigm. That's the first point I would make. The second point I would make is that in order to carry out a political agenda like that, because it's a political agenda you're suggesting, then you have to have, it's a political agenda because you're suggesting different criteria and this and that and the other, you have to show that you're right. And the third issue that I have with you is that although I absolutely agree with you about impact factors, it's total nonsense. You'll have seen the thing in Lancet Neurology the week before last, where all the editors have written to the academics saying, stop using damned impact factors. I've written to my dean with a copy of that letter saying, stop using impact factors. Right? But citations is something very different. If people are constantly referring to your work because it's helping advance the subject, then that is an indicator that means something. And if you look at citations of Nobel Prize winners and so on, you see that there's a much better correlation. So people are looking constantly at those things. I agree with you much more about the money side, because you can put down that you're a coordinator of a European project worth 10 million, and actually you're just sitting in your office coordinating it. So I agree with you about that. Public-private, I think we have absolutely nothing to say in Europe about public-private. The Americans do public, they do private, they do public-private, they couldn't care less. They put the money where the results are. And we don't do that for ideological reasons, for this reason, for that reason, for the other reason. We need to be much more subtle about the way we get our academics and our industrialists working together. This whole debacle with Alzheimer's, starting off with acetylcholine, then amyloid and so on, single agents, and suddenly everyone's piling into it. I mean, why? It's not the way it's done in other places, unless you have too much money and too little sense, and then you can pour money into anything you like. So I agree with some of what you say, but I think there's no point in being polemical about it. We just have to advance. And I would agree with you about the indicators. I don't agree with you about bad public-private. I think we need to develop those more. And I think those were your two messages, weren't they?
So I think that...
These are opinions, of course, your opinion, my opinion. We need to now work it out.
So I think that this is a very nice introduction to the next session.